Welcome to AI Frontiers, where we explore the most fascinating developments in artificial intelligence research. Today we're diving into 9 groundbreaking papers published on July 13, 2025, that reveal how robots are becoming smarter, more efficient, and surprisingly more like the creatures that have mastered navigation for millions of years. These aren't just incremental improvements, they're fundamental breakthroughs that could revolutionize everything from autonomous vehicles to delivery drones. Picture this. A delivery drone navigating through a bustling city, dodging buildings and birds while calculating the perfect landing spot in real time. Meanwhile, an autonomous vehicle threads through traffic, predicting the erratic movements of human drivers while planning its own optimal path. And deep in a research lab, a tiny robot inspired by the humble ant finds its way home using nothing more than a few grainy images and a memory smaller than a smartphone photo. Today we'll discover how robots learn to navigate like insects with minimal resources, how they manage uncertainty in real-time autonomous decision-making, and how bio-inspired algorithms are revolutionizing energy efficiency. We'll explore self-supervised learning that reduces data requirements and examine the future of human-robot collaboration. Each breakthrough represents a fundamental shift in how we think about robotic intelligence. Computer science robotics represents one of the most dynamic intersections in modern technology, where computational intelligence meets physical reality. Think of it as the bridge between the digital minds we've been building and the mechanical bodies that can act in our world. Unlike pure software that lives safely in servers and smartphones, robotic systems must grapple with the messy, unpredictable nature of the real world. Where sensors give noisy readings, motors don't always respond perfectly, and the environment constantly changes in ways no programmer could anticipate. What makes this field particularly fascinating is its interdisciplinary nature. It's like a symphony where artificial intelligence provides the brain, mechanical engineering builds the body, computer vision serves as the eyes, and control theory acts as the nervous system. Each component must work in perfect harmony, because a robot that can think brilliantly but can't move smoothly, or one that moves gracefully but can't perceive its environment, is ultimately useless. The field has undergone a remarkable transformation over the past decade. Early robots were essentially sophisticated automated machines, capable of performing repetitive tasks in carefully controlled environments. Today's robots are venturing into the wild, literally and figuratively. They're exploring Mars, navigating busy streets, working alongside humans in factories, and even learning to cook in our kitchens. This evolution has been driven by 3 key factors: the explosion of machine learning capabilities, dramatic improvements in sensor technology, and the democratization of computational power that once required supercomputers. The first dominant theme reshaping robotic intelligence is uncertainty management and active probing, teaching robots to make smart decisions when they don't have all the information. Imagine you're driving and you see a pedestrian near the crosswalk. Are they about to cross? Are they just waiting? A human driver makes split-second judgments based on body language, context, and experience. Modern robots are learning to do the same, but they're doing it by explicitly modeling uncertainty and making decisions that account for multiple possible futures simultaneously. Rather than trying to eliminate uncertainty, successful robotic systems are learning to embrace it, using strategic actions to gather information while making decisions. This approach involves strategic information gathering through active probing, where robots make subtle movements to gauge other agents' intentions. The mathematical foundation is particularly noteworthy. Researchers have developed multimodal prediction systems that can handle multiple possible futures, each with its own probability distribution. When uncertainties follow certain mathematical distributions, closed-form solutions enable real-time risk assessment that was previously impossible. These breakthroughs have applications ranging from autonomous driving scenarios where vehicles must predict unpredictable human behavior, to multi-robot coordination where communication is limited and robots must infer each other's intentions from observed actions. The second transformative theme draws inspiration from an unexpected source: insects. While we've been building robots with powerful processors and high-resolution cameras, researchers are discovering that ants and bees navigate with remarkable efficiency using brains smaller than a pinhead. This bio-inspired approach isn't just about copying nature. It's about understanding the fundamental principles that allow biological systems to achieve robust performance with minimal resources. Ant-inspired algorithms are achieving remarkable efficiency through mushroom body architectures that use minimal memory. These systems implement learning walks for environmental exploration, allowing robots to build spatial memory through structured exploration, much like ants do before embarking on foraging trips. The technical achievements are staggering. Navigation systems operating with less than 9 kilobytes of memory footprint while maintaining robust performance. This represents a dramatic computational requirement reduction compared to traditional visual navigation systems that require high-resolution cameras and significant computational resources. The implications are revolutionary. Imagine drones that can navigate for hours on a single battery charge, or autonomous vehicles that can function reliably even when their main computers fail. This research challenges fundamental assumptions about computational requirements, suggesting that the future of robotics may lie not in building more powerful computers, but in building smarter algorithms that can achieve remarkable performance with minimal resources. The third and fourth themes focus on real-time optimization and neuromorphic computing, addressing the challenge of making perfect decisions in imperfect time while revolutionizing how we process information. Modern robotic systems are developing unified frameworks that can simultaneously handle multiple objectives, avoiding obstacles, minimizing energy consumption, reaching destinations quickly, all while operating within the strict timing constraints of the real world. It's one thing to calculate the optimal path when you have all day to think about it. It's quite another to do it in milliseconds while traveling at highway speeds. Neuromorphic computing represents a fundamental shift inspired by biological brains. Traditional computers process information in discrete steps, like a factory assembly line. Neuromorphic systems process information more like a jazz ensemble, with timing, rhythm, and energy efficiency that conventional computers can't match. These systems use spiking neural networks that can achieve performance comparable to traditional neural networks while consuming orders of magnitude less power. For battery-powered robots, this could mean the difference between operating for hours versus days on a single charge. Recent research has revealed that by carefully adjusting the membrane potential leakage in these bio-inspired networks, it's possible to achieve practical performance levels while maintaining dramatic energy savings. This discovery could revolutionize how we design neural networks for battery-powered robotic systems, enabling new applications where energy efficiency is crucial. The research has produced remarkable breakthroughs that are reshaping the field. Perhaps the most significant is the development of closed-form solutions for risk assessment in uncertain environments. When a robot needs to evaluate the safety of different actions, it traditionally required computationally expensive simulations. Recent work has shown that when uncertainties follow certain mathematical distributions, it's possible to calculate risk metrics instantly using elegant mathematical formulas. This breakthrough enables real-time safety assessment in complex scenarios, like autonomous vehicles navigating through unpredictable traffic. Another groundbreaking result demonstrates that bio-inspired navigation systems can achieve extraordinary efficiency. Researchers have shown that mushroom body architectures, inspired by insect brains, can perform visual navigation using less than 9 kilobytes of memory while operating at 8 Hz on hardware as modest as a Raspberry Pi 4. To put this in perspective, that's less memory than a typical smartphone uses to store a single photo, yet it's enough to enable robust navigation in complex outdoor environments. The third major finding concerns the critical importance of fine-tuning in neuromorphic systems. While spiking neural networks have long promised energy-efficient computation, their practical application to robotics has been limited. Recent research has revealed breakthrough techniques that achieve performance comparable to traditional neural networks while maintaining dramatic energy savings. A fourth breakthrough demonstrates iterative optimization consistently outperforming existing methods in demanding applications, while the fifth involves ultra-high-frequency sensor fusion achieving unprecedented accuracy and low latency in precision tasks. The methodological landscape of robotics research encompasses several sophisticated approaches, each with distinct advantages and challenges. Sensor fusion represents one of the most fundamental techniques, combining data from multiple sensors to create more accurate and robust environmental understanding than any single sensor could provide. The strength of sensor fusion lies in its ability to overcome individual sensor limitations. GPS provides stable coordinates but has slow update rates, while accelerometers provide high-frequency data but suffer from drift. By combining these sensors using advanced filtering techniques, robotic systems achieve both accuracy and responsiveness. Machine learning-based prediction and planning forms another crucial category. Modern robotic systems increasingly rely on learned models to predict future states and plan appropriate actions. The strength of machine learning approaches lies in their ability to handle complex, nonlinear relationships that would be difficult to model analytically. Optimization-based control methods formulate robot control as optimization problems, seeking actions that minimize cost functions while satisfying constraints. These methods can handle multiple objectives simultaneously and provide theoretical performance guarantees, incorporating safety, energy consumption, and task completion constraints into unified frameworks. Bio-inspired algorithms draw inspiration from biological systems, offering efficiency and robustness developed through millions of years of evolution. Neuromorphic computing approaches use spiking neural networks and brain-inspired computing paradigms to achieve energy-efficient processing, with potential for dramatic energy savings compared to traditional digital processing. Let me take you deeper into the first transformative paper by Gadgenmath et al., which introduces a groundbreaking framework called active probing with multimodal predictions for motion planning. This work addresses one of the most fundamental challenges in autonomous systems: making decisions when you don't know what other agents will do next. Traditional approaches often assume that other agents will behave predictably, but real-world scenarios are rarely so straightforward. Human drivers might choose from multiple possible actions at any given moment, and an autonomous vehicle must be prepared for all reasonable possibilities. Their methodological approach is elegantly sophisticated. They develop a novel risk metric that integrates multimodal prediction uncertainties through mixture models, explicitly modeling the fact that future states can follow multiple possible modes, each with its own probability distribution. The mathematical foundation is particularly noteworthy. When uncertainties follow Gaussian mixture distributions, they prove their risk metric admits a closed-form solution. This is remarkable because closed-form solutions are rare in complex optimization problems, and their existence enables real-time computation that would otherwise be impossible. The active probing mechanism represents perhaps the most innovative aspect. Rather than passively accepting uncertainty, their system strategically selects actions that provide the most information about other agents' behavioral parameters. Using the meta-drive simulation environment, they demonstrate robust performance across diverse traffic scenarios, with significance extending far beyond autonomous driving to numerous robotic applications involving decision-making under multimodal uncertainty. The second transformative paper by Gatto et al. Presents visual homing in outdoor robots using mushroom body circuits and learning walks. This represents the first real-world implementation of a lateralized mushroom body architecture for visual homing on a compact autonomous robot. The research objective is ambitious yet focused, developing a visual homing system that achieves the remarkable efficiency and robustness demonstrated by ants in nature. Ants can navigate complex environments and return to their nests with extraordinary precision, using only minimal sensory input and requiring just a few learning walks to establish navigation capabilities. Their methodological approach is grounded in detailed understanding of insect neurobiology. The mushroom body is a brain structure found in insects that plays a crucial role in learning and memory, particularly in navigation tasks. They implement a lateralized architecture that mimics how insect brains process spatial information, using the sign of angular path integration signals to categorize panoramic views into goal on the left and goal on the right memory banks. The learning walk mechanism allows structured environmental learning through exploration, similar to how ants perform structured exploration around their nest before embarking on foraging trips. The experimental validation is particularly impressive because it demonstrates real-world performance rather than just simulation results. The technical specifications are remarkable for their efficiency. The system operates at 8 Hz on a Raspberry Pi 4, using only 32 by 32 pixel views and requiring memory footprint under 9 kilobytes. This represents dramatic computational requirement reduction compared to traditional visual navigation systems, demonstrating that bio-inspired approaches can achieve practical performance levels while dramatically reducing computational requirements. The third groundbreaking paper by Ren et al. Addresses self-supervised pretraining for integrated prediction and planning of automated vehicles. They introduce Plan May, a unified pre-training framework that capitalizes on masked autoencoders to achieve both behavior prediction and trajectory planning without requiring massive amounts of labeled data. The research objective moves beyond traditional imitation learning approaches that optimize against ground truth metrics, which can achieve good performance on specific metrics but often fail to develop holistic scene understanding enabling truly robust autonomous driving. Their methodological innovation lies in using masked autoencoders to learn rich scene representations from unlabeled data. The key insight is that by forcing the system to reconstruct missing parts of driving scenes, it learns to understand the relationships between different elements, vehicles, pedestrians, road infrastructure, in ways that transfer to both prediction and planning tasks. This is fundamentally different from traditional approaches that train separate systems for prediction and planning. The experimental validation demonstrates that their self-supervised pre-training approach leads to significant improvements in both prediction accuracy and planning performance across multiple datasets. More importantly, they show that the learned representations transfer well to new environments and scenarios, suggesting that their approach captures fundamental principles of driving behavior rather than just memorizing specific situations. The significance of this work lies in its potential to dramatically reduce the data requirements for training autonomous vehicle systems, potentially accelerating the development and deployment of autonomous vehicles while improving their robustness and reliability. The future directions emerging from this research point toward several exciting possibilities. First, we're likely to see increasing integration of bio-inspired approaches with traditional robotic systems. The success of mushroom body architectures and learning walk algorithms suggests that nature still has much to teach us about efficient computation and robust behavior. We can expect to see more research into how biological principles can be adapted for artificial systems, potentially leading to robots that are both more capable and more energy efficient. Second, the development of closed-form solutions for complex robotic problems represents a significant trend. As researchers develop more sophisticated mathematical frameworks, we're likely to see real-time capabilities that were previously impossible. This could enable new applications in high-speed robotics, from autonomous racing to precision manufacturing, where split-second decisions are crucial. Third, self-supervised learning approaches are likely to become increasingly important as the field moves toward more practical deployments. The ability to learn from unlabeled data could dramatically reduce the time and cost required to develop new robotic systems, making advanced robotics accessible to a broader range of applications and organizations. However, significant challenges remain. Safety and reliability continue to be paramount concerns, particularly for applications like autonomous vehicles where failures can have serious consequences. Developing robust testing and validation frameworks for increasingly complex systems will be crucial. The energy efficiency challenge will also become increasingly important as robots move into more diverse applications, requiring continued research into energy-efficient algorithms and hardware architectures specifically designed for robotic applications. This episode demonstrates how artificial intelligence is being used to synthesize and present cutting-edge research. The content you've just heard was created through AI synthesis using GPT and Claude Sonnet 4-20250514, representing the latest advances in natural language processing and research analysis. The text-to-speech synthesis was powered by Deepgram technology, showcasing how AI can transform written content into natural-sounding speech. Image generation utilized Google's AI systems to create visual representations of complex robotic concepts. While this content has undergone human expert review, we acknowledge the potential for oversight and encourage listeners to verify information through the original research references provided. This approach allows us to rapidly process and synthesize large volumes of technical research, making cutting-edge developments accessible to a broader audience. The integration of multiple AI systems, from language models to speech synthesis to image generation, demonstrates the collaborative potential of artificial intelligence in knowledge dissemination. However, we maintain transparency about our methods and encourage critical evaluation of the content. All original research references are provided for verification, ensuring that listeners can access the primary sources and form their own conclusions. This hybrid approach, combining AI efficiency with human oversight, represents a new paradigm in research communication that can accelerate the transfer of knowledge from academic laboratories to practical applications. As we conclude this journey through the cutting edge of robotics research, several key insights emerge that will shape the future of artificial intelligence and autonomous systems. The integration of uncertainty management and active information gathering represents a fundamental shift in how we design intelligent systems. Rather than trying to eliminate uncertainty, successful robotic systems are learning to embrace it, using strategic actions to gather information while making decisions that account for multiple possible futures. The power of biological inspiration continues to surprise researchers and practitioners alike, demonstrating that millions of years of evolution have produced solutions that are often more elegant and efficient than our engineered alternatives. The convergence of multiple advanced techniques, from neuromorphic computing to self-supervised learning, is creating new possibilities that were previously unimaginable. The move towards self-supervised learning and data-efficient training represents a crucial step toward making advanced robotics more accessible and practical. The robots of tomorrow won't just be more powerful versions of today's systems. They'll be fundamentally different, combining the efficiency of biological systems with the precision of engineered solutions. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archived preprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archived preprintserver.org.